It's about the time. Let's get started. So good afternoon, everyone. Today we are very happy to have Professor Mathieu Letacon from the Karlsruhe Institute of Technology giving this weekly seminar here. So let me briefly present the speaker's CV. So Mathieu Letacon got his PhD in solid-state physics in 2006. Actually, he got a couple of impressive studying experiences before starting his PhD. So from what I see, he got a bachelor and master degree in fundamental physics, and then only changed to solid-state physics in the second half of his master degree. Yeah, and then after that, he did a postdoc at the European Synchrotron Radiation Facility, ESIF, on the inelastic X-ray scattering beamline. And then starting from 2009, that was 1 year before I joined the institute, he started at the Max Planck Institute for Solid-State Research as a group leader, leading the inelastic photon scattering group. And that lasted until 2016, when he became a W3 full professor. That's the highest rank in Germany. At KIT, and he's also the founding director of this the Institute for Quantum Materials and Technologies, IQMT, which is kind of similar to our name, ICQM. Yeah, and yeah, he's specialized in using photon scattering techniques, studying correlated electron materials and superconductors, and has made important discoveries and won important prizes, including the ESIF Young Scientists Award, IUPAP Young Scientist Prize, and Heidelberg Academy of Science Prize. So today he will tell us about nematic liquid, soft-phonon, and charge-density-waveformation in this barium nickel arsenide. Let's welcome the speaker.
Well, thanks a lot for the very kind introduction. Thanks a lot also for the even kinder invitation. And it almost feels like after this talk, it's starting to be the weekend already. It's been very intense 3 days and very enjoyable. So thanks to all of you for showing me and discussing, and for the interesting discussion so far. So I adjusted a bit the title. So in the abstract I had sent, because I was too lazy, I made one abstract for yesterday and today's talk. And for those of you who were yesterday at IOP, I mostly focused on the cuprates. So today I will discuss on this interesting system, the barium nickel-2 arsenic-2, and this phosphorus doped version. But before I do that, I just say a few words of my university. I mean, so the Institute of Technology of Karlsruhe. So I'm not sure whether everyone knows where it is. So actually, this part here of the map would be France. So Karlsruhe is really at the tip of France on the German side. So for a French guy living in Germany, it's really ideal. And it is a university which is composed actually of two legs. One is the university, which was the first technical university of Germany, which was founded in 1825, which is in the city center. Here, and the second one is the research nuclear center, former nuclear research center, which has been done in the forest about 130 years later. And those two entities fused to create KIT in 2009, which right now has about 10,000 employees, closer to 25,000 students this semester, and an annual budget of about 1.1 billion euros. So it's one of the 10 excellent universities, the title that he regained in 2019, and it's a very nice place. So for those of you who are looking for a place to continue and to go abroad, we have a lot of cool stuff at KIT, and you're welcome to join. Good. So I want to talk today about this interesting compound, barium nickel-2 arsenic-2, and I'm going to show you mostly two studies. The first one is the Raman scattering study, and the second one is the inelastic X-ray study of the phonon dispersion in this material. So I need first to acknowledge a few of my colleagues, and first and foremost, Agira Gigirat, who has been growing very high and very good single crystals. The experiment that I'm going to show have been performed in part by Yi Yao, who was my former PhD student, and Tom Lackman, which is getting slowly but surely to go towards the end of his PhD. Michaela Souliou is a senior staff scientist in my lab. Michel Mertz is doing X-ray diffraction. And I had various cooperation also within the institute for transport and thermodynamic measurement. And of course, we had a very nice theory input of Rolf Heid for first principle calculation and Jörg Schmalian for the more creative modeling part of the discussion, let's see. And of course, we acknowledge also the beamline scientists who help us carry on the experiment. Good. So this is a talk about charge-density wave. So I showed this thing yesterday. I'm not going to say too much about it. And again, it says charge-density wave as the most generic way of understanding this, as there was an instability of a metallic system towards the formation of a periodic modulation of the charge density. So you start with a metal, which has heavily spaced atoms with an electron distribution which is modulated following the lattice structure. And you can have an instability, for instance, this Pyers instability, where you have this dimerization, which creates a superstructure, so a doubling of the unit cell. And you can associate that with a wavelength or a momentum, or wave vector, more precisely, that defines the modulation of the order. So I also showed that. That's the last slide that I also showed yesterday that we see. So we had the charge-density wave in the cuprates. This is what I talked yesterday. I think not everyone was here yesterday, so maybe I try this again. There's a very interesting compound here which shows also a superconducting dome and charge-density wave instabilities. And who can guess, and who was not there yesterday, who can guess which compound it is? Well, that's uranium. So just pure uranium as an elemental compound actually also have a superconducting, oops, what I did, so has a superconducting dome and a charge density wave instability. And I guess what I'm trying to show here is that there are many compounds, so the decalcogenide, which also have this charge density wave and this kind of superconducting phase at low temperature, the more recently discovered and also widely studied here, Kagome materials, which have this charge density wave which decrease with pressure and this double dome. And finally, there are many other examples, but I'm going to focus today on this one, the barium nickel-2 arsenic-2. So the reason why I chose to look at this particular compound was actually that we asked ourselves the following question. Barium nickel-2 arsenic-2 is known, it's been discovered pretty much at the same time as the barium iron-2 arsenic-2, the parent compound of the 1-2 iron-based superconductors. And those particular materials are very interesting, and there's been a lot of discussion about electronic nematicity, which is understood in this phase diagram. So the compound has at zero doping, so half filling, so the parent compound here exhibit a magnetostructural transition. So there is some kind of stripe magnetic order that forms and an orthorhombic distortion of the lattice. And before it forms, you get some kind of nematic fluctuations. And the way to understand that is that you have pretty much a doubly degenerate magnetic order at Q equal pi 0 and Q equal 0 pi on the square lattice. So these are doubly degenerate order, and nature doesn't really like degeneracy. And so you can create a new order parameter, which would read as basically the square of the parameter of the order parameter along x minus the square of the parameter along y, which tend to spontaneously take a finite value and break this rotational symmetry, so that you have de facto the system is going to choose either one or the other. It's going to favor one of these phases against the other. So this yields to nematic fluctuation. So this fluctuation between, as long as the system is in the tetracurrent state, it is not chosen yet whether it wants to go to this one or to this one. It gives rise to a domain structure at low temperature, but those fluctuations themselves, they have been widely discussed, and in particular in relation to superconductivity, and whether those nematic fluctuations could be mediating superconductivity, for instance, and more generally, the question of how they interact with superconductivity. So now the nickel compound is essentially a charge analog of the iron one, so it has no magnetic order, and it has a bit of a different phase diagram, which back in 2012 has been studied, for instance, by Kudo et al. And so this is a bit of a sad story because, you know, when you cool down that system, what you find is a strongly first order transition around 140K. So that's interesting, by the way, that this transition occurs pretty much at the transition at which the iron 1 to 2 orders magnetically. And when in this phase, what you have is basically transition from the tetragonal system to a triclinic phase. And nobody, which is a bit sensitive and likes to work a bit in the reciprocal space, likes to work with triclinic crystals. I mean, I think that the space group here is P1 bar. So you, you pretty much broke all possible symmetries. But it was also realized later on that it actually is accompanied by a commensurate charge density wave, which has this wave vector, so 1/3, 0, 1/3, but it has also 8 twins because of the triclinic distortion. So it's really a mess, the reciprocal space of that compound. Maybe I'll show it later. It has superconductivity already at 0.6 Kelvin, which is different from the iron-based superconductor. But what's interesting is that when you suppress this triclinic phase using, for instance, phosphorus doping or cobalt substitution, you have somewhat an enhancement of the critical temperature, so which goes from 0.6 Kelvin to 3.5 Kelvin, something like that. So it's still very low TC, but it's interesting. Now, more recently, the group of Peter Abamonte published this result where they actually showed that just above this triclinic transition and this commensurate charge density wave, there was another very small regime with an incommensurate charge density wave. And actually, when this paper came out on the archive, one of my colleagues came to my office and said, well, that's embarrassing. We have this for a very long time. So these are X-ray data at 160K and 110K. And so I'm not sure whether we can nicely see it, but this was measured on an image plate system. But you see that when you cool the system down here, so this is a doped compound, so the temperature is a bit lower. But you essentially have these two sets of satellites here, showed by the white arrow, that appears around the main Bragg peak. So you can nicely see this modulation. And this corresponds to a charge density wave, which now, so again, it's incommensurate, 0.2800, has another satellite at 0.280, and it's above the commensurate charge density wave. And associated with that, there's been a report for fluctuations, nematic fluctuations, but now of the B1G symmetry, so compared to the iron-based superconductors, rotated by 45 degrees. So this has been looked at with different things, and one thing that is also striking is that all those phase diagrams, they look a bit different. I mean, with strontium substitution, cobalt substitution, phosphorus substitution. And I guess what we try to understand is what was the interplay between all those charge order, the nematicity, the superconductivity. So there's been a bunch of interesting papers that have been published. So this is just for last year. So this is not as much as for, say, the Kagome superconductors. So this is something you can still follow the literature in a way. So it has some momentum. So the group of Ming Yi, the group of Birgeno and Paglione are looking into this material. And yesterday I had also very good discussion with Xi Liang and I'm not sure how to say. And Li Xing Song, so about this neutron scattering measurement on the strontium doped compound. And so again, our contribution there is what I'm going to show, mostly focused on the parent and the phosphorus substituted compound. So our approach was basically to do everything from scratch. So at the institute, we have a solid crystal growth department. We have about over 20 furnaces, actually even more now, where we can grow very nice and high quality single crystals that we can analyze also with a very, very handsome, small and versatile electron microscope to do EDX and check that the composition is fine. We recently refurbished our X-ray lab, so this is only part of the thing. So we have this 4 diffractometer. This is the new beautiful Synergy Rigaku machine. That's the one I was talking to you about. It's just fantastic, and a smart lab for the power diffraction. So that allows us to really make systematically, and actually all the crystal we look at, we always start by checking that the quality is good with X-rays, and to refine, to make an actual real crystallographic refinement to really know what we are looking at. And I mentioned here the thermodynamics group of Christoph Meingast, who is doing this capacitance dilatometer. So I just learned today that you have here even interferometry dilatometry, which is even has even better resolution and easier to use. But we're still very proud of our good old capacitance dilatometer to characterize these materials. And the story started as follows. So we looked into my colleagues Christoph Meingast and Michael Merz, they looked into these materials, which has this large trickling transition, and so they did the dilatometry measurements. And what they found is that when you cool the material down, you do see this very strong first order transition. Okay, so this corresponds to this transition here. Actually, it also has an hysteresis if you warm up. So here's just upon cooling at 137 K. So you nicely see this big first order transition. But because we have this very high resolution in the dilatometry, if we look carefully at what happens just above, we can see that there's actually a small difference in the dilatation along the nickel-nickel bond and along the diagonal. So it's a very small and very subtle effect, but it has been checked and cross-checked several times. And the only way you can understand that is that you break the rotational symmetry going from an I4MMM tetragonal phase to the IMMM orthorhombic phase. So in the iron-based superconductors, it would be FMMM phase, so it's rotated 45 degrees. But as you can see, it's really at the limit of our dilatometer. It's very small, and there's a tiny orthorhombic distortion above the structural transition. So when we first observed that, I mean, the reviewer have been quite tough, and they asked for more tests. So we looked at the phosphorus dope compound, and it turns out that in the phosphorus, I have to stop that. In the phosphorus compound, I think this is more obvious. Huh? You nicely see now a second order phase transition above the trickling transition. So you suppress a bit the trickling transition temperature, and you now nicely see this. And so we thought, okay, now there's clearly evidence for this orthorhombic distortion. And we can look into that in more detail and try to learn something. So before I show you what I did myself, I just want to point out that Christoph published last year a very nice and complete thermodynamic study of the doping dependence, so proposing this phase diagram here. I'm not going to enter the details, but basically you see all those phase transition. If you look at the orthorhombicity here, so in the dope compound, where it develops a bit more than in the parent compound, you can see the type of distortion. So just to give you an order of magnitude, it's about 10 times smaller than the distortion that you see in the iron-based superconductor. So it's really not big, but it's measurable, and I think it's quite clear that you see this difference between A and B. So you have signature of this even in the heat capacity, so you actually see that it corresponds to an actual phase transition, and also in the resistivity. So I'm not going to enter so much the details here.
So the resistivity is actually not behaving dramatically, right, across these trends. I mean,
no,
more like a gradual change.
Yeah. I mean, these are all very small changes. So I mean, frankly, if you look at the resistivity the first time, you wouldn't notice it. I mean, it's just you have to know from somewhere else it's there. So one question that also came is really, can we see that with X-rays? And it turns out it's very hard with X-rays, and so you really have to use the highest resolution setup. So in that case, we went for we used our four-circle diffractometer. We close all the slit. We go for a large reflection, and indeed, instead of seeing this nice point reflection, you can see that there is some kind of spread corresponding to the domain formation in this compound. And so for the 800, this looks more like this, and for the 448, this is this spread as you would expect for this kind of distortion. And again, this is something you can only see in the doped compound, where the distortion is established. So when I came in, was basically to try to learn more about the distortion and to first see whether it's real. So this was before we did this X-ray measurement and these things. And the approach I took was to do scattering. So that's another slide I showed yesterday. So the idea is to start with an incident particle, to have this particle scattered by the system. During the scattering process, the system is brought from an initial to a final state. There is eventually an energy and a momentum transfer. we'd have to satisfy the conservation law. So the energy has to be conserved, so you can create some excitation in case you have an energy transfer and you look at the dynamic of the system. But you can also look at static correlation, or the structure if you look in the elastic channel. And you have some momentum transfer, which allow you to either probe homogeneous correlation, so Bragg reflections, for instance, and you can look at the structure of the system by diffraction, or inhomogeneous correlation and probe the dispersion of your excitation if you work at finite Q different from any Bragg wave vector. And for today, we mostly used this inelastic scattering in two regimes. Regime number one is that of visible light. So this is a setup which is very similar to that of Yuan here. It's a small Raman spectrometer where we work with incident energy of 1.5 to 4 electron volt. So this is a very long wavelength. So that's pretty much probing the excitation at the zone center of the system. But it has a very good energy resolution. So typically less than 0.1 milli-electron volt. And with this, we are mostly going to look at phonons. But in principle, you can look at other kind of excitation. Turns out that in this particular system, phonons are the main degrees of freedom I'm going to focus on. Now, if you want to go away from Q equals 0, you have to use a photon which has a higher or shorter wavelength, so carries a higher momentum and allows you to transfer some momentum to the system which is reasonable compared to the size of the Brillouin zone. And so this we do using inelastic X-ray scattering. So we go at the synchrotron beamline and we scatter inelastically photon in the kilo electron volt range, tens of kilo electron volt range, with an energy resolution of 1 to 3 electron volt. There again, there are many kind of excitations you can look at. Elastic scattering is a zero energy loss channel, so it's a kind of diffraction experiment, but with energy resolution, if you like. But we're mostly going to focus here on the phonons in the second part of the talk. So, going back to the history of this distortion here, the tetragonal distortion. I just want to show the example of the iron-based superconductor. So this system again has a tetragonal symmetry, and from the group symmetry you can make you can look at which are the allowed phonons in the system, and you have 4 Raman active phonons, A1G, B1G, which are C-axis polarized vibration, and you get the EG mode, which corresponds to the in-plane vibration of the nickel and arsenic. Now, what happens when you go across the tetragonal to orthorhombic transition is that you lift the degeneracy between A and B. And actually, these modes, they are EG modes, so the E means that the mode are doubly degenerate. It means that the vibration, the planar vibration along X and the planar vibration along Y have the same energy. Now, if you distort the system in an orthorhombic manner, you will lift this degeneracy and you will see a splitting of this doubly degenerate mode. So this was looked at early on by the group of Alain Sacuto in Paris, but there was also some nice work done here by Yuan. And the bottom line is the following. So these are the earlier data. The quality is not really good, but I think it already shows what happens. So you have a single peak here, and when you cool down, you see 2 peaks. You just see a splitting of the peak. And if you look at this splitting, it's actually not a small splitting. It's a splitting that amounts to a 9 wave number for a mode that has a frequency of about 130 wave number. So it's a splitting of about 9%, 8% of the mode frequency. And compared to the size of the distortion, this is actually a fairly large splitting. The distortion of the system is of the order of 0.1%. So you have 0.1% difference between the A and B lattice parameter, and it lifts the degeneracy of your phonon by 8%. So this was understood later on as a consequence of the coupling to the magnetic degrees of freedom. But what's interesting is that you can look at the temperature dependence of that splitting. So that's now the difference between the upper branch and the lower branch as function of temperature for different doping along the dome. And you nicely see this kind of order parameter-like shape. The point I'm trying to make here is that if you look at this splitting, you can actually look and follow the orthorhombic distortion. You can compare that, for instance, with dilatometry measurement. So these are the PhD work of Anna Böhmer, which was in my institute before I arrived, and now is a full professor in Bochum. And she did dilatometry also on this compound, and I actually use this thing, and you can scale. So you get the parent compound, the 4.5% and the 5%, cobalt doped system. And you can translate these two things one onto the other, and you can basically see that they match very well. So the phonon splitting really is, in that case, a measure of the orthorhombic order parameter, or said otherwise, of the nematic order. Nematic order, I insist on that. So we thought, okay, in the nickel-based compound, we do have a structural distortion which is 10 times smaller than in the iron-based. But in the iron-based, the effect is so large that even a 10 times smaller effect we should be able to detect in Raman. So we started looking at those phonons in this barium nickel-2 arsenic-2. So this is the same structure, so these are the same selection rules. So you get 4 Raman-active phonons, A1G, B1G, and 2 EG modes, which are doubly degenerate. So we can measure them. So it's a lot of fun to measure the EG mode because you have to put yourself on the side of the sample, and you need a very high spatial resolution, which is allowed by the micro-Raman spectrometer that we operate. But in short, that's how it looks. So you have the A1G mode, you get the B1G mode, so in that case, then you see the both together. And if you get the cross-polarization on the side, you see nicely the 2 EG phonons. There are a few things that are already remarkable. I mean, this EG phonon is quite soft and it's quite broad. But for the moment, we just ignore this, and we cool the system down. So first, I go to 50K, and then at 50K in the parent compound, I am in the triclinic phase. Triclinic phase at this awful 3x3 commensurate charge density wave and this triclinic transition. And so, yes, I can see immediately, without understanding anything about the spectrum, I can see that I'm in the triclinic phase. There's no doubt about that. Okay. Now, what happens above the triclinic phase then is more interesting. So I look at this A1G mode, and you see that it's nicely sharpened and hardens as any good phonon should do. The lattice contracts, the vibration of the lattice gets stiffer, and the anharmonic effect decays, so the phonon lifetime, which is inversely proportional to the width of the phonon, decays. So the A1G mode behaves absolutely as it should, and this is great. Now the EG mode, this doubly degenerate mode, is a different story. First, it starts to soften, which is not normal when you compress a system, or when you cool a system down. Most of the time, when you contract the lattice, the phonon hardens, so it's kind of already a strange thing, and then it splits. So we were happy. We were looking for a signature of the splitting. We were looking for a signature of the orthorhombic phase, and there we have it. Wait a second. Let's look at the numbers, because on the barium 1 to 2, I had a distortion of 3 to the minus 3, the orthorhombic distortion, so that's the difference to the A and B, so 0.3%, and I had a split of 9 wave number. In this nickel 1 to 2, I have a distortion which is at least 10 times smaller, but my splitting is at least twice larger. And if I look at the relative splitting, so that the phonon here is quite soft, it has a frequency of 40 wave number, I have a splitting of 50% of the mode's frequency. In the case of the barium 1 to 2, the iron compound, it was called a giant splitting. And I'm not sure what is the word we should use for this kind of splitting in that case. Because relatively speaking, you have a distortion which is 10 times weaker and an effect which is at least twice larger. So it is at least 20 times larger. And if you think in terms of relative value, which, okay, is arguably a bit cheating, but it is a 50% splitting, so it's an order of magnitude larger effect. 2 orders of magnitude larger effect, sorry.
But how about the higher energy EG?
The higher energy EG also split, yeah. Mm-hmm. It splits less, but there's a good reason for that.
Okay.
So that has been somewhat puzzling us for some time. And it has been puzzling us furthermore that if you look carefully at this line shape here, the onset of the splitting occurs definitely well in the tetragonal phase. And we came up with the story that we were dealing with an electronic nematic liquid, and the key word here is liquid, and I'm going to tell you how we got there. So just to convince you first that what happens here is not normal. Sorry, I made this control plot. So I'm comparing here again the thermodynamic measurement with our data. So again, we can nicely see when we enter the triclinic phase, and we can also see that the effect, and I think on this contour plot this is very clear, the effect onset well above this kind of tiny orthorhombic distortion. So that's something which is very weird. We looked at it a bit more carefully as well. Now that's why we went so particularly with the phosphorus doping. So in the phosphorus doping, where the distortion, the orthorhombic distortion increases when you map it out and try to follow it. Okay, that's what happened as function of doping essentially. So we looked at it with resistivity, and as I said, in resistivity this is a very subtle effect, and actually we saw first something in the derivative of the resistivity, but we're not so sure that this actually corresponds to this. Now we also look at the incommensurate and the commensurate charge density wave peaks, and same thing, the onset basically is always occurring above the temperature at which we can see with our lab diffractometer the formation of the charge density wave, and this is true for all the doping. So, and if you see this one, the 10%, 10%, you're basically outside. I have troubles with this one. Okay, sorry. So with the 10% dope, we are here. So there is no structural transition anymore. And yet you see this nicely, this splitting. So the higher energy mode, the splitting is more subtle, and is actually more seen as a broadening, at least at the low doping. And here it mostly looks like a broadening, but harder to see to resolve two peaks. But we nicely see, at least in the lower and the higher doping, and down to the lowest temperature, we have this completely lifted degeneracy. So, and again, this onsets well above any of the phase transition that we can see with conventional thermodynamic method. So I put this on this phase diagram here, and that's the onset temperature of the splitting, and it has this weird thing. This is where the incommensurate charge density wave is detected as an order. This is where we see the orthorhombic distortion. And actually, in that 10% compound, we don't even see an orthorhombic distortion. So we see no difference between A and B. We see a small thing happening along the c-axis. I'm not going to say too much about it, but pretty much this guy here is completely tetragonal, yet you have this large splitting of the phonons. So this has been really puzzling us, and that's where York-Schmalyan come in the game. I say, well, I have a tetragonal compound, and I have this splitting of the EG mode. What causes that? And then his answer was very easy. He said, well, there's no splitting. And what you see is actually a coupling, the effect of the coupling of your mode with some nematic fluctuations. So it was a fairly bold statement, but it didn't come out of the blue. And in a nutshell, he made a very simple toy model to try to account for that. And the idea is that you take two degenerate phonons. So here is the harmonic oscillator for your two degenerate phonons. They have the same frequency omega 0. And you couple them to an Ising variable that describe a nematic degrees of freedom. In short here, what you see is pretty much you have two degenerate states. So basically a distortion along A, or so A is the long axis or B is the long axis. And you can call this a spin up and this a spin down. So these are your two eigenstate of this nematic thing, and you allowed tunneling between these two states at a rate omega. Okay, so you get a tunneling rate between these two configurations. And you couple those fluctuations here to your phonon with a coupling constant lambda. So what Jörg liked a lot in that story is that actually this is a very simple toy model, and it actually can be solved analytically, and it can be solved analytically also at finite temperature. So that doesn't mean it's easy, and it takes Mathematica to work a bit, and that's actually only one part of the function. So you have this 80-line formulas, and you can solve this up at finite temperature. But the result is actually this, if you compute that. So it's a non-trivial many-body problem, but that can be solved analytically also at finite temperature. And what you see by increasing the ratio of the coupling constant to the mode frequency is that you will see a splitting of the mode. But the splitting here that you see it when the expectation value of this Pauli matrix tau z is still 0, meaning that you don't have long-range order. So in a regime where your system is still completely fluctuating, there's not long-range order, you can see the splitting of the mode. And again, it's not a splitting in that case, it's just a change of the line shape of the phonon, which reflects this coupling. And of course, if your coupling is too strong, what you will go into is an actual phase transition, so you will order the system. But there is a whole nice set of regime where basically when the coupling is large enough but small compared to the typical frequency of the phonon, where essentially from the phonon point of view, it's just like if the system had this degeneracy lifted. So you can think of the phonon as a finite frequency probe of the dynamic of the system. And your phonon at low frequency basically sees that the mode splits like that. And that's also why if you go to higher frequency phonon, the splitting that you see or the change of the line shape gets smaller. Now, what is also very nice is that basically from a formal point of view, this has a strong analogy with the spin liquid problem, because you typically have a strong fluctuation between degenerate configuration without long-range order. And that excited Jörg quite a lot. But I have to say, not the editor much. So we had to soften some of the things. But in principle, if you think of it, in the regime where you can bring this kind of fluctuation down to the lowest temperature, you can end up in a system where you do have a quantum nematic liquid, and then you could expect some funny physics to occur. So of course, this kind of modeling came with a bit of prediction. The first one is that there should be some signature of this nematic fluctuation in the electronic Raman spectra. And those should be stronger in the B1G channel compared to the B2G channel. So this we checked, and indeed we found that the electronic Raman response showed some enhancement compared to the in the B1G channel compared to the B2G channel. So the B2G has a kind of mild metallic response, which is somewhat boring, and the B1G shows a somewhat broader response, this increase of intensity. And I just want to say that compared to what happened in the iron-based superconductors, this is very broad. This extends over a very large energy range, which is somewhat unusual. But essentially indicates that those fluctuations are overdamped and suggest that they are indeed coupled to something and very likely to the lattice. The second prediction or postdiction, which is quite interesting here, but it was a prediction on data that we already had but that they hadn't seen. So it's a pre-postdiction. Is that, well, if you have a tetragonal system and you do have those fluctuations, but you should not be able to detwin the system because there is nothing to detwin. In the iron-based compound, you can glue your sample onto this kind of substrate, which has an anisotropic thermal expansion, and that is sufficient to align all the domains of the sample. What Jörg said is that, well, that should not work in that case, and in particular if you're in the tetragonal phase, because at least if you're in the limit of a small distortion, you should not see an effect. So just to illustrate, so these are the data from Yuan that we copied for our paper, and that was replotted by our theory colleagues. That's why it doesn't look so good. But essentially now if you look at the EG mode in the ordered phase of iron selenium, I mean, if you apply some stress, you see either one or the other. You don't see the two. As soon as you put some stress, you detwin the system, you see one or the other mode. If we do the same thing on the nickel 1 to 2, You get a small spectral weight redistribution, but you're never capable of completely suppressing one peak or getting the other, despite the fact that we are using pretty much the same kind of distortion here. So with this, well, we were quite happy, and basically what we concluded from that is that this large EG splitting, despite being so large, is the signature of a purely dynamical effect that we call the electronic nematic liquid state in the nickel 1 to 2. So I've not been doing so bad so far, and I can just switch to the last part of the talk, which is the origin of the charge density wave. So I started this talk saying that one thing that was interesting in the system is that we had this incommensurate charge density wave, but so far I have not really said much about it. So this was studied by the group of Peter Bamonte when they looked at the incommensurate charge density wave. So this forms, but this seems to form at a temperature which is a bit above the temperature of this tiny orthorhombic distortion. And so we tried to understand how you relate this orthorhombic distortion with the charge density wave. So one thing that had been overlooked in the early studies, so people have been early on calculating the phonon spectra of this compound based on DFT calculation, but you know that with DFT you overbind a bit and you tend to have a crystal structure which is a bit too small. And when you do that, you basically don't see any instability. Now, as part of our procedure here, we determine experimentally the lattice parameter, and we like to provide our theory colleague Rolf Hyde this crystal structure for the calculation. And then he can run his DFT calculation of the phonons based on the actual lattice parameter that he can relax. And that gives usually an excellent agreement with the experiment, and that's what he finds. So he can calculate the lattice dispersion, and then you can see that now there's a mode which happens to be unstable at a momentum which is quite close to that of the charge density wave. What's interesting, so you can also calculate the electron-phone coupling. You can see that there is a strong electron-phone coupling for this mode that happens to be the A1G mode that I showed at the beginning, and that actually has a small Fano line shape for those of you who have the sharp eye of the Raman spectroscopist. So that's where most of the electron-phone coupling comes from. That being said, this low energy mode, which is the EG phonon, also has some electron-phone coupling, much smaller. And it happens that this is the same mode that we see split at low frequency that become unstable at higher Q. So that's interesting in itself. I would just like to point out here that we, of course, asked Rolf at the beginning to check what kind of distortion it would take for him to see a lift of degeneracy of the phonon here of the order of 3 millielectron volt, as we see in the experiment. And that's basically impossible for him. I mean, he can never get there. So there's no way. I mean, the kind of strain he has to apply on the structure is of the order of 10% or more. Which doesn't make any sense. So now we had this prediction of this unstable phonons, and we thought it would be good to check. So for this, what we did is to use the inelastic X-ray scattering beamline, but the side station of that beamline, which can be used to do X-ray diffuse scattering. So this pretty much consists in looking what's happening between the Bragg reflection. So what you do when you do this inelastic X-ray scattering experiment, you look at the dispersion of some phonons. So this is your scattering cross-section. I explained it better yesterday, but in short, you have a form factor that modulates the intensity across the Brillouin zone. You have this polarization selection rule in a way which allows you to select the phonons which are polarized along the momentum transfer you're looking at. And you have this delta function which picks up the phonon at the energy where it is. Now there's this 1 of omega term, means that if you integrate over the energy here, if there is a phonon that is softer than it should be in the dispersion, it will appear as some trace in your diffuse scattering map. So this is just the energy integrated part of this thing. So we can use this to locate ourselves in the reciprocal space and to before starting looking at the phonons. We can also calculate the structure factor, of course, for the phonon in the calculation, and we did some temperature dependence in elastic scattering around the 411 Bragg reflection. That's where we thought we had the biggest chance. So what we see here is basically the Bragg reflection, the 411 Bragg reflection, and you can see that around it you have this nice diffuse satellite. So there's no way you can see that in the lab. Okay, so this is very weak, it's very diffuse, very broad, but with this kind of machine you can of course see it, and you can see that along the z-axis you have this nice modulation here along the z-axis. So this is the HK1 plane, and this is the 4 KL plane. Okay, so you see, and so these are this corresponds to the diffuse scattering associated with the phonon. So we can look at the diffuse scattering as function of temperature, and what you see upon cooling is that this diffuse scattering becomes stronger and stronger, and at some point it becomes so strong that it's actually as strong as the Bragg reflection. Okay, and so this is pretty much the region where we start seeing this in the lab machine, and then we can look at it in the plane and perpendicular to the plane. We can also analyze the line shape of this diffuse scattering, and it's quite interesting. So if we look along the L direction, what you have at high temperature is a strong diffuse background, which can be nicely fitted by a Lorentzian function. And as you can see, as you cool down, the peaks get sharper and sharper, and actually, at some point, you cannot fit this with a Lorentzian background, and you have to use the so-called super Lorentzian profile. And this super Lorentzian profile, in a nutshell, what it tells us is that we do have still this diffuse background, on top of which we have a real resolution limited Bragg reflection. Okay, so this is a criteria from which we can see when we still have the fluctuations and when the order appears. In a nutshell, when you cannot fit your fluctuation profile with a simple Lorentzian, it means that you have a real Bragg reflection and you have a long-range order. So we looked at it carefully, and what we found is also quite surprising. We can look at the width or the inverse width, or the width of the peak, which is the inverse of the correlation length in the plane and out of plane. And you can see that in the plane it is fairly boring. It's decreasing, so the correlation length is increasing in the plane, but nothing very specific happens. On the other hand, there seems to be some kind of critical behavior, albeit with a weird exponent here, along the z-axis for the out-of-plane correlation. And that's where now the intensity looks like. And you can compare this transition temperature with the thermal expansion coefficient or with the elastoresistivity, for instance. And you can nicely find where the CDW long-range order takes place and how it compares with the orthorhombic distortion. Long story is that the orthorhombic distortion occurs just below the temperature at which, but within 1 or 2 Kelvin. So you have the condensation of the charge-density wave, the long-range order that forms, and then you have the orthorhombic, this tiny orthorhombic distortion that forms. Now, we also tried to look at whether there was a soft phonon. So this is in this Brillouin zone, 411 around so in the transverse direction from the 411 reflection. So we can basically see it. So this is the structure factor that is calculated. So we have an optical branch here. So we see this optical branch that disperses pretty smoothly. And then at lower energy, we have this already very soft phonon. So remember, these measurements are done with a resolution of the order of 3 millielectron volt. And it can be somewhat complicated to fit it. So you have these damped harmonic oscillators. You have to take into account the resolution effect. And you have this elastic line, which is also increasing, but somewhat hard to get exactly the thing. But it just turns out you can just fit this profile with the phonons. And what's interesting is that at the wave vector of the incommensurate charge-density wave, you can clearly see well above the transition, you can clearly see that the phonons are very soft. And because of this 1/omega in the scattering cross-section, when the phonons are very soft, the intensity becomes very large. So we can fit that and we can follow this and then try to look at this as function of temperature. And this is really tricky now because with that kind of resolution, basically what you see upon cooling is a very strong central peak. So the way to see whether the phonon is completely soft or not is to compare this profile here, this inelastic scattering profile, with the resolution in gray. And you can see that from 270K, where there's clearly a softening, and below roughly 160K, we cannot really distinguish. It seems to be a bit broader than the resolution, but it's really, really hard to extract from that a meaningful energy associated with that. I mean, you can get a number, I just don't believe it. I mean, you can get a slightly different number if you make a slightly different analysis. So I prefer to be conservative, say, well, the mode soften. And we try to constrain the fit quite severely with the spectral weight of the photons and things like that. But still, it's a bit too, below 160K, it's basically impossible to distinguish anything. You just get this very strong elastic line. So this is quite clear that indeed we are dealing here with a soft mode-driven charge-density wave. In parallel to our measurements, there was the group of Birgeneau also published a very nice study with somewhat higher resolution, from which they basically claim that the full softening of the mode is occurring at a temperature which is already larger than that at which the charge-density wave really forms. It might be, it might not be. I mean, that's their claim. And based on the data that we obtain, we can just not conclude whether this is true or not because we don't have sufficient resolution. Now, regarding the origin of the softening, well, we can get some insight again from the first principle calculation. And so the way to look at it is, I mean, we can look at the joint density of state of the system. So that's basically an indication of whether there is a Fermi surface nesting. And you can see that at the Q of the wave vector, at the Q of the incommensurability, there's pretty much no structure, no particular structure related to the Fermi surface of the material. You can calculate the phonon line width, which is a measure of the electron-phonon coupling, and this is actually the sum over all the line widths of all the phonons. So this is really the total electron-phonon coupling. And well, there is some kind of thing at that wave vector, but it's very shallow. I mean, that's basically the cut here. I wouldn't really call that a sharp maximum or a divergence or really strongly momentum-dependent feature. And actually, there are many more features at other Q which would deserve that better. And you can basically look at the electron-phonon matrix coupling element and the anisotropy of the element by taking the ratio of these two quantities. And again, here you do have some kind of maximum, but it's a very broad maximum, very shallow, and it's not particularly remarkable into this direction. I mean, if this would cause an instability, why this not, why this not, why this not? I mean, there could be instability over the place. So in long story short, it doesn't look like the electron-phonon coupling in this particular system can be the driving force for the charge-density wave, which we believe has a different nature. In echo maybe to what we discussed on Monday, where we had also done some collective mode spectroscopy together with Jure Demsar in Mainz. And what he found is also somewhat surprising result is that those charge-density wave excitations, they are very strongly resilient. And you can use a very large fluence and very strong laser intensity, and you basically hardly kill them. So they survive also, they're very, very, very robust. I just finished on that with some more I mean, we have more than these speculations, actually. We do have some evidence that indeed the orbital degrees of freedom are playing a role, but we had our early X-ray absorption data. So if you look at the dichroism of the X-ray absorption, so polarization independence of the X-ray absorption as function of temperature, what you can find is that there is a spectral weight transfer between the in-plane and the out-of-plane orbitals, which is associated with the formation of the charge-density wave. And that basically indicates that what we call in that case a charge order is probably more of a funny manifestation of an orbital polarization in this metallic system. I will skip this, but we also done some elastoresistivity measurement, which is interesting, and that's just the last thing I want to show. So we are revising that paper now. It's going to be accepted. Again, it gives us a very hard time. So we looked at the pressure dependence of the different charge density wave in this compound, so using X-ray diffraction. The only thing I want to show here is this yellow part. I show at the beginning of the talk many phase diagrams, including charge density wave and superconducting dome. And in all of them, you had a decrease of the charge density wave transition temperature as function of pressure. I know very, very few examples of a charge density wave transition temperature that increase with pressure. There are a few, but maybe 5% of the total charge density wave system I know. A system where the incommensurate charge density wave doesn't care about pressure, I've never seen. So there's something very strange here, and so we, I mean, this ordering charge density wave transition temperature around 145 Kelvin or something like that remains pretty stable up to 7 GPa. So that really tells us that this kind of phase here is not a normal charge density wave. It's a different beast. And I'm just going to stop here, and thank you for your kind attention.
Thank you very much for the interesting and clear talk. Now the floor is open for questions.
So you have the CW1, RNE1, you said does not care about the pressure. Then I also see this plateau for the incommensurate CW2. Is it also flat there? So
that one is a completely weird, so it's a completely different incommensurate modulation. And so we don't have so much here about the temperature dependence. So yeah, we plot it this way, but okay, we know that it's still there. I cannot tell you much about the onset, the offset here. So we just have really this point here with the temperature dependence. You know that when you play with diamond engine cell in the temperature pressure range, in all of this so these are 2 or 3 beam times together. Unfortunately, you cannot explore this map as you would because the pressure is sometimes a bit complicated to control. So I cannot really say here what's going on. But so we mostly looked at it from the isotherm, and then we just have a few isobar, and basically here we have only one isobar. And here you always have the problem that if you go too high in temperature, well, we didn't want to go too high in temperature, so I don't know. But this one is super weird. I mean, I can show you more after that about the shape. I mean, it has a completely different pattern, and it's and the underlying structure is actually a monoclinic structure. So it has some kind of a collapse monoclinic phase, we call that. Instead of having a collapsed tetragonal phase, you have a shear motion of the nickel arsenic planes against each other.
Maybe I can ask the next question. So actually 2 questions. So so since you explained of this EG's line shape because of this coupling, I was wondering whether that mechanism can be like verified with like isotope effects, like replacing whether it's supposed to be very sensitive to how the lattice works. That's the first question, and the second one is I think very early you show some color plots showing the magnetic susceptibility, indicating the phase transition for the phosphorus doped sample. I was wondering whether magnetic field could control this behavior in any way.
So so 2 things: isotope effect. What could we learn from the isotope effect in that particular case? I'm not sure. I mean,
since it's completely dynamic coupling, right? So I was guessing that changing the mass would change the
when we do the phosphorus substitution, we change the mass of part of the oscillator because it involves, of course, the nickel and the arsenic motions.
Yes.
The renormalization of the frequency is not that crazy, actually. And we could think of a different kind of substitution. So if isotope effect, you mean substituting the nickel by something else.
The real isotope, yeah.
Or if you want to just change the nickel isotope by another nickel isotope.
Yeah, just the nickel isotope. Yeah, the same
Yeah,
chemical.
okay. I have to admit here, I don't know enough about the nickel isotope to tell you
to
whether
completely like prove that this dynamic coupling story is true, whether it has a unique prediction on that frontier.
Okay, I would have to think about it.
And how about
I don't know.
Yeah.
And
how about magnetic field? Yeah.
And the magnetic field. So actually, in the measurements by Peter, they characterized the transition here using the magnetic susceptibility.
Yes.
And this was measured actually with 1 Tesla.
Okay.
So you see this order here. So this is 1 Tesla, and it's a very weak signal. So actually, magnetic susceptibility is not that great to study the system. It really doesn't show any magnetic order, which, by the way, has been confirmed recently by Marc-Henri Julien, which looked at these samples using NMR, and can definitely rule out any kind of magnetic order in that system.
I see.
So the nickel is just not magnetic in this case.
I see. Thanks. Yes.
So in the first part of your talk, you were saying that you have the electronic nematic order developing far above the structure phase transition, while structure is still tetragonal.
Yeah.
So besides this easy mode splitting, do you have any other evidence that you have this charge nematic order? That's the only experiment you have.
Well, first of all, it's the only experiment, but I really want to emphasize again how not normal this experiment is. I mean, this splitting is just absolutely unacceptable. So it needs to come with some reason. So from the thermodynamic point of view, we don't see a real signature of that, and the only thing we can really see, maybe I have it here in the paper of Christophe. What seems to occur here in this range is some kind of fluctuation in the C/A ratio. So the take-home message here is that in all these kind of systems, the C/A is very important in controlling the electronic phase of the material. And the only thing that we see at high temperature here is a deviation from an already anomalous behavior. The C/A ratio is increasing with cooling, but the rate at which it increases somewhat seems to step down here. It doesn't tell us anything about whether it's a nematic and something like that, but that's the only other evidence we have that something is happening above those transitions from the structure. But the structure remains really tetragonal. I mean, and this is a very, very tough judge of whether the system is tetragonal or not. I mean, thermal expansion. If you don't see, you have this high resolution, right? So, when thermal expansion tells you the system is tetragonal, it's really tetragonal.
I guess you need to measure the in-plane properties, just rotating, with respect to one axis, the A or B axis, you see some kind of twofold symmetric.
Yeah, I think in his system, the resistivity and magnetic susceptibility show only weak signature for the transition from the beginning.
They show weak signature of the actual transition. So any regime above this transition are very hard to detect. So we want to think a bit of what would be another smoking gun. I mean, Jorg has came and proposed a 3-color experiment, nonlinear photon, so how do you call that, 2D spectroscopy, that would actually be able to distinguish between this nematic liquid and any other kind of ordered phase. And it works very nicely on the paper. The problem I see, and that you probably see when I tell you about doing this kind of spectroscopy here, is that it's very strongly metallic. And that my terahertz radiation is hardly going to penetrate the thing.
Yeah, the rotation of the polarization may be actually very sensitive to the charge electric order.
I have to think about it. Yeah.
So
I wonder why there is no nematic order, yet the nematics are actually very strong.
You can call that orthorhombic distortion the nematic order, if you like. Okay, this is a very tiny nematic order. Now why is it so? Why, given this insane effect on the phonon, why is the distortion so small? This is a very good question. I don't know. I mean, it seems that all that nematicity in that case is really carried and driven by the phonons, more by the electron, and not so much by the electrons. So the electrons are somewhat following the phonons here, but do not seem to be the main driver of this nematicity. That's also what's suggested by the elasto resistance measurement, that do see a signature of a B1G nematic fluctuation, but nothing which is critical, and that would be associated, for instance, with unconventional superconductivity at low temperature, and also nothing that is really strongly involving the electronic degrees of freedom. So all the anomalies, if you want, they are seen, for instance, in the heat capacity, in the phononic term of the heat capacity, where there is a very strong softening of the modes, for instance. And the electrons themselves, they seem just to be there as some kind of spectators. It's a very...
So we can call it like lattice.
Yeah, I guess something a lattice nematic, yeah. But you know, it's...
But that's orthonormicity. Lattice nematic, is it the same or the different?
Except that it's dynamic here. I mean, again, I mean, I really, you know, I mean, the term liquid is the best thing we could come up with in following the notion of generalized liquid. You know, you do have a state which does never completely order. From the formal analogy of the problem at the analytical point of view with that of the spin liquid. Yeah, we had discussed that with Andrei Shubukov, and I showed him, oh yeah, that's a liquid, that's a liquid. So we had very good feedback on this, but it's a very strange thing, and probably, yeah, the phonon here is the main driver, but still doesn't really tell me why are those phonon line widths so broad also compared to what you get from the calculations. So I think we're really missing something when it comes to the orbital degrees of freedom, and we've been trying to look into that a bit more, but it's a bit unusual to have this kind of orbital polarization, say, in a metallic system, as far as I know, at least.
Far?
So I think you showed that the density function of perturbation theory
Yeah.
calculated this phonon and solid
Yeah.
instability. So why do you say you still don't know the origin of this instability?
Well,
The density function theory seems to be able to explain it.
no. The dimensional function theory finds that the structure isn't stable. But there's nowhere in the output of the calculation, there's nowhere something that tells you why it's unstable. That's the drama. I mean, I don't want to call this a black box, but yeah, you can look at the structure, you can put the actual lattice parameter of the structure, and find that the structure is unstable against the softening of a certain phonon. But it doesn't tell you why this phonon is so soft. And Rolf has been trying to play a bit around this and try to suppress the thing, and it just also couldn't really, yeah, that's a bit. So I agree with you. It's a nice thing that, you know, the theory predicts the instability, but the theory doesn't tell us here where the instability is coming from.
Well, I think, for example, they should be able to compute the dielectric function. So that will tell you, for example, the electronic contribution to the phonon.
Yeah, actually, this is a good point. I mean, yeah. Well, we haven't done that yet.
Although you showed that the total John density state and some other thing didn't show strong feature at this way.
Well, I mean, in a sense, it really contrasts, for instance, with the instabilities that you would have in niobium diselenide or a classical charge-density wave system. Even this lanthanum silver antimony compound that we measured from here, where you can nicely see the instabilities and the soft modes and follow them as function of temperature. Yeah, so here, we can certainly do more in this direction. I mean, I have to admit, I mean, there was always this discussion, you know, and it's not that I eluded it, but it is also at home a delicate story. I mean, technically, the Fermi surface nesting that we look at is the imaginary part of the charge susceptibility. And what we would like to have is the real part. But now the real part has to involve all the, so in other words, you can have the divergence of the electronic susceptibility if you have some nested part of your electronic structure, even deeply in the occupied state, which is something I really don't understand. But there's an argument that was brought out by Mazin, I know, 15 years ago, and apparently there's a theorem that says that Mazin turns out to be true. And so I tried to get Rolf calculating for me the real part of the susceptibility, and he's very reluctant to that because basically it says that you really have to integrate over all your electronic bands quite deep in the dispersion. And that could give us some hints there as well, but I found a new way. Actually, I couldn't sleep this night, and I thought of it, and I think, we just make the joint density of state at different frequencies deeper in the dispersion, and that he cannot tell me no. But yeah.
Yeah, but from the from the merit of the optical spectroscopy, and the material here is absolutely is not a standard charge-density wave.
Well, but again, you're referring to the 1/3, 0, 1/3 commensurate charge-density wave, or?
Yeah, the charge-density wave basically for these materials, the structure phase transition, you actually see the spectral change over very broad angular scale. That's if it's charge-density wave, basically you see a kind of gap opening just below, something like that's no energy physics. But here, we look at this material, it changes over maybe several EV or something. So it's not no energy physics here after the phase transition.
Yeah. No, this is this is a very interesting point, and again, it brings me back to discussions we had recently with the editors of several journals about what we should call a charge-density wave and what we should not call a charge-density wave, and I think this has to be clarified. In a way, I, as a reply, I also asked ChatGPT, what is a smoking gun for a charge-density wave? And the first answer was, it's a superstructure in a metallic system. So I'm happy with that, but obviously this is not because you see a superstructure that there's not a richer physics. So that's a bit...
Maybe the reason why so many things are changing in the optical spectrum is because it's like a first order phase transition. Yeah.
It would be interesting to relook at, because again now we had this huge first order transition, and the temperature range at which this nematic liquid thing happens is just above the first order transition, which is not, again, if we had not knew it was there, I'm not sure we would have run this detailed Kelvin after Kelvin temperature measurement in a 10 Kelvin range. It can be easily missed. So maybe just to revise those measurements in this, either in the narrow temperature range above the trickling transition, or in the phosphorus dope compound at 10%, where there you don't have a trickling transition. This would be very interesting and in my opinion, very insightful as far as the physics of that incommensurate charge-density wave is concerned, and to decide whether we can call that a charge-density wave or not.
So let's see if there are any questions from the students. We have student questions. If that's not the case, okay, one, yeah.
So, colleague just behind did a very beautiful neutron scattering experiment on the strong compound, and we were supposed to do that. We had so yes, the short answer is yes. In an ideal world, I would have been able to show you some data today, but unfortunately, someone screwed up with the alignment of the mosaics, and we switched to a backup sample.
Another system.
So of another system, but we will look into that with neutron also more carefully, because actually neutron is the best to get the highest resolution and to really see what's going on in this region. Now we can do that much better.
And I guess also one aspect that makes it a little different from standard CDW is the dip is pretty broad in momentum space.
Yeah,
like
well, I mean, okay, this one has to be a bit careful from the calculation because it depends also a bit of the interpolation scheme and the things like that. So there's always a bit, one has to be cautious with that,
yes. Okay, since we don't have more questions, let's thank Professor Le Tacon again.